Welcome to this new Midas Civil webinar called Stay Tuned Practical Cable Stayed Bridge Design. My name is Francesco Incelli and I will be hosting this webinar today. Talking about the contents that we're going to go through today, I'm going to do a small introduction on cable stayed bridge design, followed by some consideration on how cable stayed bridges can be modeled in Midas Civil, with a brief note regarding the bridge wizard and also how the cross-section for the girders can be imported or modeled in the software as well. I will then proceed with a discussion regarding the nonlinear effect, which are quite critical for this kind of structures, at least for the big span cable stayed bridges, and then show how the initial cable forces can be calculated using two main functions that the software provides. One is the unknown load factor, and the other one is the cable tuning. Regarding cable stayed bridge design, the major characteristic of a cable stayed bridge are the fact that the deck acts as a continuum beam, and the effect of the stays is to provide isolated spring supports, which have varying stiffness due to the fact that each stay has a different length and different angle. The deck and the pylon, they are both in compression, and the bending which is added to them is increased by a P delta effect. So it has some second order effect that will have to be considered. This is an important consideration to be done because the influence line method, which is based on elastic superimposition of stiffnesses and loads, can be used just as a preliminary or approximate method for determining the stay loads. And this is much more evident if you're doing like a hand calc of it. With modern technology, though, there are ways of going around it and taking account the P delta effect straight away when you're doing the determination of the cable pretension, and we will have a look at that. And also something very important for cable stayed bridges are the non-linear material properties like creep and shrinkage, which can affect sometimes consistently the calculation and determination of the cable stays, because on top of the intrinsic nature, non-linear nature of the structure, we are going to add things like creep and shrinkage, which are going to increase the level of convolution of the calculations. So the key word when you approach a cable stayed bridge is iteration. So you're going to do a lot of iterations on finding the right geometry, finding the right loads, and identifying the stiffness of the deck as well. If we want to discuss how the design process of a cable stayed bridge is developed, we can summarize it in 10 steps, which start from the determining the backspan to mainspan ratio, then the cable spacing, following with the deck stiffness and the pylon height. Then we can proceed determining the preliminary cable stayed force, identifying what's the best deck form, do the deck design, and once that's sort of finalized with a number of iterations, we can move into checking the construction of the deck, of the structure, which means doing either a backwards or forward analysis, and we will see what that means. And then proceed, once that's finalized, we proceed with doing static analysis, for example, moving load analysis or any type of load which is additional to dead loads and permanent loads in the structure. And then, if required, a dynamic analysis. Design step 1 is related to how to determine backspan to mainspan ratio. And this is very important because the size of the backspan ratio influences the uplift force for the mainspan, and it influences also the range of load within the backstays cables supporting the top of the pylon. In general, in many structures, the optimum length of the backspan, so in the picture that you see on the screen, the dimension A, is going to be in between 0.4 or 0.45 the main span. So it's almost a half of it. Regarding the cable spacing can be determined based on the capacity of the longitudinal girders to resist the bending in between the stays, and also the load limit for the stay itself, which means the number of stays will have to be decided in relation to what's the available size of stays which can be provided and their relative capacity. So we can't really think to apply just like a couple of stays because the load in them could be much higher than what can be withstood by the biggest available stay that can be manufactured. And also the spacing should be small enough to allow the deck to be erected using cantilevering method. That's another parameter that influences the design. Regarding the deck stiffness, the deflection of the longitudinal girders are determined by the stay layout, which means that those deflections that are controlled by the stays mainly. The depth of the girder should be kept to a minimum. A way to determine the area and the stiffness of it is to make sure that the deck can resist the large compressive forces produced by the stays, and it's mainly designed in buckling. So the first way of determining what's the size of the deck is actually to do a buckling check on it. Regarding the pylon height, the height of the pylon will determine the overall stiffness of the structure because the stays angle influences the stiffness of the stays. In general, the most efficient stay angle is 45 degrees. So we should be aiming to have that kind of angle. And in practice, the efficiency of the cables is not significantly impaired if the cable stays in between 25 and 65 degrees. The consequence of the limitation in angle for the stays is that the height of the pylon above the deck level is roughly between 20 or 25% of the length of the main span. Regarding the preliminary stay forces, the main span stay forces resist the dead loads such that no deflection of the deck or the pylon occurs for the permanent loads. An initial approximation, if you're doing like a hand calc or using a known computer assisted method, is to approximate the full structure as a truss, ignoring the bending stiffness of the pylon and the deck. And that's the first approximation that you can do to get a feeling of where you are heading to, what type of order of magnitude of the load you can have. The backstay anchoring forces can be calculated assuming the horizontal component of the main span and backstay forces are balanced at the pylon. Regarding the deck form, the primary factor influencing the choice of the deck will be the length of the main span and the deck width. In general, as a rule of thumb, concrete deck sections are suitable for span range in between 200 and 400 meters, and composite decks above 400. Above 600, then a hybrid combination can be done, which consists in back span made of concrete and the main span made all in steel. Regarding the deck design, one of the main parameters is the deck bending. So one of our main concerns should be to minimize the moment in the deck under dead loads, and we can do this by tuning the loads in the stays to reduce the bending produced by the overall layout of the stays. The balance between positive and negative live loads moments at any section along the girder will not be equal, and in most cases the properties of the deck section will be more favorable when resisting positive moments than negative moments. Regarding the construction stage, the common method for deck erection is the cantilever method, so that's very common and quite convenient in terms of saving temporary works and allowing for the construction itself. The stay force that are compatible with the final distribution of the dead load moments and the defined structure geometry are known. However, the force at each stage is not known. That's why construction stage is required. The way of determining this deck erection load or the stays erection load are backward analysis or forward analysis. In the backward analysis, you just operate a progressive dismantling of the structure, so going backwards from the finished state to the initial state. And then so the forward stage analysis takes in account the actual construction sequence of the structure, and it starts from the initial stage and ends to the completed stage. After the forces are determined for the permanent case and construction stage as well, we can proceed with the static analysis. doing a moving load analysis and applying all the rest of the loads. For the static analysis, one of the most common approaches is to model either half of the entire structure as a space frame. The pylon and deck and the stays will usually be represented with within the space frame model by line element or truss elements. The stays can be modeled with a small inertia and a modified modulo of elasticity that will mimic the sag behavior of the stay. And if dynamic analysis is required, then this consists either in seismic analysis of the structure, response spectrum analysis of the structure to wind, for example, and also time history transient analysis of vibration. A quick way of modeling cable stayed bridges is to use the wizard. So the wizard allows to model symmetric or asymmetric bridges, to use truss or cable elements, and also it allows you to model box sloped girders and to arrange the spacing of the vertical station. When it comes to modeling a cable stayed bridge, a lot of attention must be paid on the elements which are selected. So let's just go through the different type of elements which software can handle, highlighting what are the differences and what we should expect if we use one element more than another. So truss element is widely used for modeling cables, and the truss elements, they provide uniaxial tension and compression behavior only, which means that the element undergoes axial deformation only. It doesn't undergo lateral or shear deformation. And it's the type of element which is mainly used to model space trusses or diagonal bracing. So the stiffness of the truss is always going to be the elastic stiffness of the E modulus, so the Young modulus, times the area divided by the length of the element. This is not the best element to be used for modeling cables because, as we said, the stiffness of those elements is highly influenced by the force which is applied into them. Equivalent truss elements are slightly better because they are tension-only elements, so they simulate what's the behavior of the cable. They're not capable of transmitting compression, but just tension forces. And by using those elements, the software will consider the axial stiffness change due to the sagging effect. So if we look at the bottom of our slide, we can see why the stiffness of a cable is different from the stiffness of a truss. So the stiffness of a cable is the result of a combination of what's the elastic sagging effect and the elastic stiffness of the truss. If you want to model cables, then equivalent truss elements or tension-only trusses are the ones to be used. For nonlinear analysis, then the software allows for a more complex type of element to be handled. And in that case, this is called the elastic catenary cable element, which is the most accurate element to describe a cable. And it reflects the change in the stiffness varying with the internal tension forces, so the sagging effect. But also for large displacement effect, the stiffness is at each step calculated based on the tangent stiffness of the cable element applied to the geometric nonlinear analysis. For modeling the girder cross-section, there are different ways of doing it. If the section is a bespoke section, you can import that from an AutoCAD DXF file through section property calculator, and you can also draw the section in section property calculator or in one of the standard built-in property generation tools in Midas Civil. And with SPC, which is the section property calculator, you can also model bespoke sections with up to 3 different parts, which can be activated in 3 different stages as well. Just a little remark on nonlinear effects. We already discussed what's the sag effect along cables. So the stiffness of the cable is influenced by not only the length of it, but also by the tension and the weight of the cable itself. P-delta effects can be included in the analysis, and P-delta effects are quite critical for the deck bending, and those can be included even if you're doing a linear analysis. You can include P-delta effects only, and the software is going to run on the background some iterations for calculating P delta effect. Then if you want to do a large deformation analysis, what you will have to do, you have to switch from, in the analysis option from linear analysis to nonlinear analysis, and in that case the P delta effect is going to be included. You don't need to run a P delta analysis on a nonlinear analysis because that effect is going to be captured straight away. One of the most critical operations for the design of a cable stayed bridge or cable structures in general is to determine the initial cable force. In Midas Civil, there is a very handy tool which is called unknown load factor, which is a function that optimizes the tension in the cables at the initial equilibrium position, which allows you to determine what's the optimized arrangement of forces in the cables based on some constraints, which can be displacement, moments, reactions for beam, for nodes, for trusses. The options available to run the optimization are linear, square, or maximum, absolute. Then you can also select the sign of the unknowns. So the factors that are going to be calculated from the unknown load factor can be either negative, positive or negative, or positive only. That depends on what you want to achieve. And also, if the constraints are input as equations with a single values, not as range, you can use the simultaneous equation method, which is basically a linear algebra method for finding the solution of the cable. So what the software does, it produces what's called the influence matrix for the cable, which is something very similar to what would be the influence analysis for moving load analysis. The table is actually drawn showing what's the influence line for one cable at a time, and the solution is found using this matrix. Obviously, if you had to do this by hand, it would take a lot of time, and there's not going to be too much value in doing it by hand, honestly. But we don't have to fall into the mistake of over constraining the problem since the beginning, because you might realize that if you apply too many constraints on the unknown load factor, then this is going to affect the likelihood of finding a solution. What I'm trying to say is that before applying constraints on every node or every beam or every cable that you have in the structure, start from some significant and relevant nodes, and if the solution is found, then just proceed with increasing the number of constraints. In the example that I'm showing there, you can see how the constraints are set up on the top of the pylons and at midspan. So that's a reasonable starting point, because what we are interested in controlling, as we said before, is that the tension in the cable is not going to produce any deformation or any major deformation on the deck and the pylons. If that's successful, then what I can do, I can try to increase the constraint conditions. So I can try to increase the constraint, the nodes which are constrained, and maybe add a few more nodes on the deck to be constrained as well, or add a few more nodes on the pylon to be constrained as well. If that's successful still, I can try and reduce the constraint range, which means if I had set up a constraint of, I don't know, of plus or minus 50 mil, I'm going to reduce that to plus or minus 25 and see if I can find a solution. So even if the software provides tools for saving a lot of time in doing iterations on the calculation, a bit of judgment and iteration that in which the engineer is the main actor will have to be done anyway. So when we are using a unknown load factor, we should be mindful that if we are using cable elements, as we said, the cable elements will be converted into equivalent trusses, and the stiffness of the cable is going to be influenced by the tension in the cable. but we still don't, when we set up the model, we didn't know what the tension in the cable was. That means that if we are using equivalent trusses, as we should do, a step that's required after having found the force with the unknown load factor is to update the pretension force in the cables so that the stiffness of the cable is updated. We can perform the analysis again and check whether the constraints are satisfied or not. This is really important because imagine you are starting your calculation of the forces for unknown load factor with a value of, I don't know, 10 kilonewtons in a cable. 10 kilonewtons in a cable, it means that the stiffness of the cable is going to be much less than the same cable stressed at 1000 kilonewton. So if I realize that after running ULF, which is the short name for unknown load factor, the tension in the cable is, as it would be, 1000 or 2000 or 3000, what I will have to do is to update the pretension that I had input and perform the analysis again and check the constraints. Only in that case I will make sure that the stiffness is correct and the tension is accounted correctly, or at least the stiffness of the cable is accounted correctly. What I can do, if still the constraints are not respected, I can run ULF another time and then repeat the same process. Update the newly found pretension forces, perform the analysis and check the constraints. So what you see on screen now is a typical outcome that you would be expecting. So the first image at the top shows the bending diagram of the deck before the optimization done with ULF, and the bottom picture shows how the bending is being optimized or changed with the optimization. Something to notice is that in here you can see how the hogging moment is quite high and almost comparable with what's at midspan. But after the optimization, it was possible to reduce the sagging quite a lot, but still the hogging in that position is still quite high. And this is what I was trying to tell you before, that in general, hogging moments can be controlled to a certain extent, but you will realize that they cannot be controlled with only with the cables. The cable tuning reduces the repetitive computation process to obtain the optimum cable pretension and calculates the effect of the cable pretension on the displacement through the influence matrix and updates the results in the graph in real time. So that means then cable tuning is quite an effective tool because in real time you can change the force in the cables, and we will have a look at how it works, and you can see straight away what's the effect of that change in the influence matrix and in the, I don't know, bending diagram or displacement diagram. So the process of doing a cable force tuning is, first of all, adjust the cable pretension using the table of the bar graph, then select the result item for which the effects is to be checked, which means select whether you want to check the diagram of the deflections, the diagram of bending, shear, whichever is the effect you are interested in. At the same time, you can see for the cables you have selected a green line showing what's the influence line for it. And you can save the adjusted pretension forces as a load combination or apply the pretension into the model and run it again. So let's have a look now at the practical application of unknown load factor and cable tuning and see some differences and some advantages of the one over the other. What I've prepared here is a simple bridge, which could be, I don't know, pedestrian cable stayed bridge, but something really simple for showing purposes, with 5 cables and like a concrete deck and concrete pylon as well. Let's switch to the wireframe view and let's have a look at what I've done to model the structure. I'm not going to go into the full detail, but what is important to see is that every tension in the cables is assigned, any pretension load is assigned to a different load case. This is very important because in order to allow cable tuning or a non-load factor to recognize the loading in a cable and to assign to that single loading a factor, is having the pretension load in an assigned load case for each tendon. So tension in tendon 1 is going to be in a load case called tension 1 in this case. Or the name is irrelevant, but this is the way I called it now. Tension 2 is going to be in another load case called tension 2, then 3, 4, and 5, and so on. Another thing to notice is that this model includes the self-weight, and it includes some additional loads, which can be superimposed dead loads or construction loads, any sort of permanent loads. It's a very simple but representative example of how to start designing the cable forces. So once the force is set to 1 for all the tendons, what I'm going to do, I'm going to run the analysis. And once the analysis is run, I will start unknown load factor. So this is the elastic model without any construction stages. And it's what I call the permanent stage model or permanent case model. In the combination tab, what I'm going to do, I'm just going to create a combination that I can call combination 1 with the self-weight, the second type of permanent loads, and all the pretension load. In the section which is called bridge within the results tab, if we click on cable control, we get access on the 2 functions which are for cable design, and it's going to be unknown load factor, the one we're going to look at now. To add a new analysis, we just click on add new. We will have to select, let's move some windows away. We will have to select the combination that we want to analyze first, and it's going to be combination 1. The combination is going to be shown in the window, which is right at the bottom of the input tab. And you can see now the factors are all 1 because these are the factors that I set up in the combination. But as you might imagine, we don't know what's the tension in the cable, and we're going to set up these factors as unknown because I want the software to calculate what's the amplification factor to be applied on tension 1, 2, 3, and 4 to reach the equilibrium solution for the constraints that I'm going to set up. Regarding the constraints, there are different ways of setting up a constraint. What you have to know is, first of all, what's the number of the element or the number of the node you are going to constrain. Let's have a look at the ones that are prepared, and then I will show you how to prepare how to apply and create one constraint by yourself. Constraints name can be any name that you like. Constraints type, it can be reaction, displacement, truss forces, or beam forces. For reaction, it's going to be node ID and the direction of the reaction. Then the type of constraints can be equality with a single value, or it could actually be a constraint in between 2 nodes. So I can select that, for example, the reaction on one node can be the same of the other node. And this can be done for the displacements as well. So I can bind together the constraints for 2 nodes to be equal. Inequality is to define an upper bound and lower bound. If you don't define a lower bound, obviously the software is going to find any solution in that beyond that lower bound. But if you want to restrict to a range, you just specify what's the minimum and what's the maximum. Another way of applying the constraints is to use the table format, which is quite convenient because instead of having the constraints in 1 by 1 in an input window, you can see the full input on a single table. And for the displacement, we can see how I created constraints for node 106, 1, 4, 8, 12, 16, 20, and 22. 106 is constrained in the dx direction, so in the horizontal direction, and the maximum minimum displacements are 0.05 and 0.05 minus 0.05. Same range of displacement is specified for the other nodes, but this time in the vertical direction. Before doing this, let's have a look to nodes numbers and element numbers. So as we said, 1, 4, 8, 12, 16, and 20 are the nodes attached to the cables. And 106 is the top node where all the cables are converging on the pylon. Regarding the element numbers, all the deck is numbered from 1 to 21. So I'm going to use those numbers to identify which are the beams to be constrained. Let's go back to our unload factor and name it as ULF. Every ULF case that you analyze has to be named before running it. Object function type, I'm just going to leave it as linear. I'm just going to click positive for the signs of the unknowns because I don't want the tension to be negative in the structure, so I don't want it to go in compression. So displacement, I'm going to use these ones that I've created, but also what you can do, which is quite useful, you can copy those into Excel. As long as you keep the format as it is, then you can modify and paste those values into the table. So for example, if I were to add more nodes, let's say I want to add node 15, for example, what I can do is to write DZ node 15. That's going to be 15. Then I can copy all of that into that row. And what I'm going to do, I'm just going to copy the full table. I'm just going to go back to that model there. I can delete the full set of constraints and then copy them in again. So as you can see, that constraint is being added to the list of the available ones. It is much faster than actually inputting them here. And now the constraint is available on there as well. In order to run this first run of ULF, I'm just going to apply the restriction for displacement to those nodes. So nodes from 1 to 22 are the ones that I've created, including node 4 and node 8. And then node 106. By clicking on Get an Onload Factor, you can see how the software calculates a factor for each of the tension cases, and those would be added to a combination. So what I can do, I can click on Make Load Combination and name it Deck Displacement, for example, 1, and click OK. If I now go and show the deformations and click on Displacement Control, I just want to see the displacement in DZ, and I want the legend, I want to see the values of those displacement, and the combination that I'm going to consider is the one that I've just created, Deck Displacement 1. You can see how all displacement at each node have a value which is within the range that I specified. My range was a maximum of 50 mil, and this node here has a maximum of 50 mil. But this is not the end of it, because I will have to update the forces that I've just calculated to the present model in order to for the software to recalculate the stiffness. But let's see how we can do it with cable tuning instead. So in order to use cable tuning, what you need to know is the combination that you are looking at. In this case, is going to be the one Deck Displacement 1. That's the one that we just created now. And you need to have a set of results. In order to create a set of results, what you can do, you can create a graph for the displacement in the x direction of the pylon, or as I've done here, displacement in the Z direction for the deck. So these are the displacements associated with this combination. If I activate influence, I can see the influence line for the load case that I've selected. Let me click on tension 1. I can see what's the influence line for tension 1. Tension 1 seems to be quite irrelevant for the deflection, but if I click on tension 2, I can see how this is quite even. But look at tension 3 and tension 4. So tension 3 and tension 4, they have the influence line for them on this side of the structure is quite significant. That means that any change in the value of tension 3 or tension 4 is going to affect this displacement more significantly than any of those ones. What I can also do, I can show at the same time two different types of results. So let me show the deflection of the pylon associated with the same combination. I'm gonna also plot what are my references, so the displacement, 0.05 for the minimum and 0.5 for the maximum, show range, and the red line, dotted line shows what's the range. I'm gonna do the same for the pylon and show range. And changing the values for the tensions, I can see in real time what's happening. And specifically, let's say I want to reduce this tension from 2,155 to, I don't know, 1,500. That's what's happening. So as you can see, deflections on the pylon, they are going beyond the limit. So I'm just going to go to 2,500. That's it. That's quite good for the deflection of the pylon. Tension number 2, let me see if increasing it to 1,200 is still reasonable. And that seems like the case. Tension number 3. Tension number 3, I want to put it to 2,500. Yeah, still within limit. And then this one, 2,000. And that one can be 1. So the cable tuning is, once you study analysis with ULF, you can fine-tune the cable tensions in order to achieve like a better result, or in order to better control the results as you would like to. Obviously, a tension of 1 in this cable doesn't seem to be reasonable, so I'm just going to increase it to 1,500. But then again, look, the displacement at the top of the pylon, they go beyond my range. So let's see what happens with 1,000. And I can sort of carry on this way. If I realize that there are no ways for me to apply a value which is different from 0 to tension 5, and having displacements for the pylon which are within the limit, that means that the condition that I've set up for the problem, they're not compatible with the tension that I want to put in those cables. So as you can see, a non-load factor finds the minimum better solution for that type of problem, but then I can fine-tune based on what would be the requirement, for example, of tension in the cables. So if I want to have round numbers for those tensions, then I can do it, or I can modify them, and I can also control what's the deflection. Now, with using cable tuning, I can either save a load combination, or what I can do, I can update the present model. So I can click on update present model. The analysis obviously is going to be changed, and the pretension value is going to be rearranged as well. And this is pretty important because I will have to do it to make sure that the stiffness of the cable is recalculated, and then run the analysis again. And for example, what I can do, I can go into the previous unknown load factor combination that I had created, and just rerun this time, keeping combination 1, rerun the unknown load factor. Still, there are factors which are different from 1. So what I'm going to do, I'm just going to make a load combination, which I'm going to call ULF2, and OK. I'm going to open up cable tuning again, loading this time ULF2 and showing the X of the pylon and then the deflection of the deck, showing the influence line as well. And what I can do, I can update to the present model, and these values now they are updated. What I'm going to do, I'm going to run the analysis again. And let's check what kind of displacement we are getting now. Combination was combination 1, because now I have updated the tension values in the cables. And look, now the stiffness has been updated. I've rerun the ULF to make sure that all the constraints are respected, rerun the analysis, and as I can see, displacement for this combination, they are now within the limit. So if my main requirement for this bridge was to limit the vertical displacement, these pre-tension values, they're fairly optimized for that. If I want to restrain the bending, what I will have to do is to show what are the elements that I want to control. And in order to do that, I'm just going to see the bending diagram for the deck in combination 1, which is the one that we're using now. And as you can see, the bending is quite high in this range here and quite high there. So what I'm going to tell the software is to control the bending in elements 7, 8, 11, 12, 15, 16, 18, and 19. Okay, let's keep the nodes visible so we can use them when we do the unknown load factor. I'm just going to create a new analysis, which is going to be ULF-Y. And let's see how the constraint is set up. So for each of those elements, I'm telling the software to find a solution which provides a upper bound bending of 5,000 and a lower bound bending of 6,000. So I'm keeping the bending to an average level, which is, according to the pre-assessment that I've done, the bending that the section can withstand. I'm going to put tension 1, 2, 3, and 4, and 5 as unknown, and then put elements 3 and 4 as constrained, elements 7 and 8 as constraints as well. Then elements 15 and 16, 17, 18, and 19, because this area is the one where I can see most bending. And yeah, it should be enough for me to run a ULF. This is not what I want, because that's a negative value. So what I'm going to do, I'm just going to restrict to all positive values and see if there is a solution. And that's what comes out of it. So tension 1, 2, 3, 4, 5. Obviously, I will have to sort of tweak this value for tension 2. But in the meantime, I'm just going to make a combination which is called ULF-MY. And click OK. I can also try and increase, for example, the level of constraints. Now I'm going to restrict element 14, 13, 12, 11, and 10, and then get the unknown load factor again. Or I can proceed by restraining element 2, 20, 21, 4, 5, 6, and 9. and that's it. This is what I get. So let's now have a look to the diagram with the combination that we just created. So ULFMY is the one that we created, and that's the bending there. So you can see how the bending is being reduced in some areas, as expected for the hogging especially. The hogging moment cannot be controlled that much because the more the tension in the cables, the higher is going to be the hogging at that location, but the sagging is completely changed, as you can see. Cable tuning can allow me to do the same thing. So I can load the combination, which is ULFMY, and I can plot the deck bending, and I can also show the influence values of the cables. And as you can see, tension 1, any increase in tension 1 is going to increase the graph in this area and decrease the graph in this area. So it's going to increase the hogging there. So I don't want to do too much on it. We're going to change this value, which is now 0, we're going to change it to 1 because it's unreasonable to have a cable which has a 0 force. And I can tweak these values again. So if I want to reduce the bending in this area, what I'm going to do, I'm going to decrease this value to 1.2. And you can see how the graph is adjusted. And let's have a look here. Let's say I want to reduce the bending, the hogging here. I can simply reduce the tension there to 3.2, for example, and that's gonna go down. Also, the sagging is going to increase. So this is another way of having a look in real time at what sort of changes you're going to apply to the model with the cable tuning. And once you are happy, you can either save the load combination or update the present model. And if you do that, then those forces are updated and you rerun the analysis. If I'm gonna go and see now the displacement, let's have a look, because the main requirement for my ULF now was the bending, not the displacement. So, but just for the sake of curiosity, let's have a look at combination 1, and let's see the values of the displacement. Now the values of the displacement, they're still within the limits that I set up. So potentially, if I set up the constraints both for the displacement and for the bending, a solution could be found. And let me just check. Unknown load factor. I'm just gonna open the file that I had just created, and I'm going to apply. So we restricted elements 11, 12, all of these ones substantially, with the exception on number 2 and all of those. And actually I can get a solution. So this is exactly the way of proceeding in identifying a proper solution for your ULF, because I started from the displacements and I've seen that there was a solution. I started from, then I proceeded with identifying a solution for controlling the bending, and now I have increased the level of constraints to both bending and displacement and found another solution. So what I'm going to do now, I'm just going to make a load combination, which I'm going to call ULF B displacement and MY. I'm going to close all of this. I'm going to open that combination in cable tuning, show range, and then I'm going to show the same deck displacement that I've shown before with the influence line and plot the range. So minus 0.05 and 0.05. Right, so I can see how using ULF and cable tuning, I can control quite easily what is the bending on my deck, what is the displacement of the deck in this case, and I can see it graphed on the screen. So the elements which I had constrained, they have bending which is within the limit that I wanted. I cannot really control the full diagram of the bending because some of the inference for these tendons for the cables is not relevant for elements which are positioned in this length of the bridge. But still, this combination sort of satisfies many constraints that I want to. And what I can do, I can update to present model. Yes, these values can be seen there straight away, and then run the analysis. Now what's left to do is just to go into displacement and have another look at what are the values for the combination 1, which is now the combination that we're going to use. And those are perfectly within the limits that I set up. Then I'm going to have a look at the diagram, my combination 1, apply, and now you can see how for those elements in which I set up the constraints, like this one, that one, and that one, and that one, all the bending is within the limit that I wanted. And this, in my opinion, according to the requirements that I had set up for this example, is an optimized arrangement of the cable tensions. Then the next step would be to move into a construction stage analysis, which I'm not going to show as we're running out of time. The next step is going to be to create a construction stage analysis to know what's the tension in the cable at each stage. And we could use the same process using a non-load factor to see what's the optimum tension to verify some constraints at certain stages. But if you have any curiosity, or if you have any question, or if you want me to explain this to you, to send you some more reference materials, then feel free to get in contact with us. That's in a nutshell what the software can do in terms of allowing you to juggle in between the sometimes tedious process of determining what's the tension in the cables, which is the optimum solution for your constraints to be verified. And if you have any questions and feedback or suggestions, please send an email to uksupport@midasusers.com and follow us on Facebook, LinkedIn, YouTube, Google+, or Flickr, and connect to our website, which is en.midasusers.com. Feel free to ask any questions. I'm more than happy to clarify any possible doubt regarding the use of ULF, because if you master to use them, and if you understand how they work, they can save you a lot of time, and they also give you a good understanding on the structure that you are designing. Have a good day, and hope to see you next time to another Midas webinar.